There are a couple of things that I just wanted to sort of hammer in again to make sure that you guys understand it. So the concept of attention, right? This is the most important the most important intuition to have in how transformers work is that it contains a function that for a given element in a sequence, so when you think abstractly, it's elements in a sequence. When you think specifically for NLP, it's words or tokens, which often are words, but aren't necessarily words. So for a given element in a sequence, for a given word in a sequence, how important are the other words around it in the sequence for understanding the meaning of it? That's the highest level idea of what's going on in a transformer. And the way that they specifically implement this is through the attention mechanism. So down here, this slide is sort of illustrating that, and it's a very messy flow chart here, showing what's going on. But at the highest level here, at the very bottom, words are being fed in, or these are E, which stands for encoding or embedding, because if you recall, the first step is it's taking every single word in the vocabulary that that given transformer model supports, and it's converting them into some initial dense representation, which is some sort of like learned word vector. So for example, they could use word2vec to initialize it. Then it is repeatedly updating that to these E primes. So like you're going from E1, and then you're mixing the information from all the other tokens in the sequence to get to E1 prime. And it's mixing more information from words that are more important than information from words that are less important. That's at a super high level. And the reason why we can only describe it at such a high level is because it's a neural network trained through backpropagation. So we can't really describe exactly what's going on. We can give intuitive descriptions for how it works, but really the model is fitting to, optimal parameters just based on the training objective that it's provided. So if you just have this flowchart on its own, nothing's going to happen. But once it acquires the correct weights, and this FFNN, that stands for feed forward neural network. Same thing here, feed forward neural network. And the self-attention here, that's this key idea of it's mixing all this information together. So what we're showing here is that specifically for E2 in the sequence, the self-attention mechanism is checking. It's doing this mapping. I believe CMP stands for like query and key mapping, but it's using that query and key mechanism that we talked about last week, and I'll go over again. Just to ensure that you have this understanding. I wish there was some way. No, that doesn't really help. Okay, whatever. So I don't know how well you can see this because it's just so tiny. Like I can barely even see it. But the key idea is that in this attention mechanism, it can have different heads that learn mappings for the importance of specific words. And the thing is that because the network is learning these word specific or embedding specific query key value mapping, each word's given things that it will look for, in other words, will be dependent on what word it is. I'm sorry, this is so high level, but in the case of I kicked the ball, when we want to know what kicked means, there are different bits of information. There are different elements of the sentence that are important for having a good representation of what kicked means in context. So, this is showing, okay, who did the kicking? That's a relevant part for understanding. Like, for example, if we blanked out kicked in the sentence and wanted to fill it back in, what information would we need to know to pick the correct word to fill in? Well, one of them is we actually need to know who's doing it, because if it's I kicked the ball, or if it's I kicked the ball versus he kicks the ball, right? You need to know who did it in order to know which conjugation of kick actually gets filled in there. Additionally, if it's the ball and you're trying to fill in the word, odds are it's going to be kicked or maybe through, but it's not going to be ate. You know, it's probably not going to be I ate the ball. It's probably not going to be I licked the ball. But if it was ice cream cone, then it could be I ate or I licked the ice cream cone. So the reason why I bring in this idea of what information from the other words do we need in order to know how to fill it in connects to William's slides from the most recent one. So this is where just having the attention mechanism on its own, it could represent any function, but the question is, how do you get it to represent a function that captures good contextual information? That's where we train on these different language modeling objectives. So the slides here that William's using go take a very like historical perspective where he's saying, okay, this was the first idea people came up with, Elmo, you know, and they did not use transformers. Then they came up with BERT where they're doing a similar thing with transformers. And that's like very high level and very historically focused. But really what we care about is just what is going on that makes it work. And within these slides here, I think this shows pretty clearly what the training objective is. So, wait a minute. Does this slide clearly show it? What they train in the case of BERT is, okay, I have slides for this. They specifically train it, given a sequence of words. Come on, come on. So this top example here is showing the BERT training objective. So given some sequence of words or sequence of elements, in this case, A, B, C, D, E, right? We're going to hide some of them from the model. And then the training objective that we're optimizing on it is given this multi-class where every single possible word in the vocabulary you support is a possible output, predict which one correctly fills it in. And then the more confidently and more correctly that it predicts them, the higher the, or the lower the cross entropy loss is going to be, right? If you guys remember that. And then the model gets rewarded for predicting them. So what this leads to is that naturally the model starts as it sees many, many examples. It sees many examples of I blanked the ball. And if it guesses licked, that's wrong. So it gets penalized for correlating licked with ball. But then it sees I blank the ice cream and it guesses licked there too. This time it gets rewarded, right? It gets rewarded for correlating licked with ice cream. So over time, as you train on many, many examples by doing this language modeling objective, eventually it learns to correctly correlate the right words with the right other words. And that's how you get these better and better representations. And the core point of having, oh, fuck, I should not have hit escape because it's gonna, let me see if I can just do slide. Okay, I don't want presenter view. I just want play from, it's gonna put me in presenter view anyway. Okay, actually presenter view is pretty helpful for me because it lets me skip right to a specific slide. So you've also seen this diagram before, right? So this is the diagram from the Attention's All You Need paper. And I'm sorry for everyone who's here last week. I'm going over it again, but I think it's probably still helpful to get it covered again. We're doing this attention operation multiple times, right? So we have embeddings in, embeddings out. And the idea is that as this information gets updated, more and more detailed information, more and more high-level information gets learned by the model. So maybe it needs to know, you know, for just I licked the ice cream, it can use very low-level like correlation of words. But maybe, you know, it was a really hot day, so I went to buy a blank. And maybe the answer is still ice cream, right? I think it's pretty easy to assume that more high-level understanding is necessary to connect the idea that on a hot day, the kind of thing that you buy is going to be an ice cream or whatever else, you know, a popsicle or whatever, okay, I don't need to get too bogged down on this example, but the point is that higher level information can get captured the more layers that you provide. And it turns out that this architecture with that objective works very well for that masked language modeling objective. So that's the masked language modeling objective, which BERT specifically is trained with. And that's what this diagram here is showing. And additionally, when you train just the encoder, which is just the left side of this transformer network, because the transformer network has a encoder and decoder side, which I'm sure you've heard before, but maybe you don't really understand. The idea of just the encoder is that we're taking the words in and we're updating the representations. They're getting encoded more and more and more. And then at the very top of the network, we have good representations of the words that, because it's been trained on this masked objective, every word is combining information from the other ones in a very useful way for predicting it. And it turns out that a good way to predict a word tends to be looking at all the other words around it and combining that information together. So then when you have that model, it's going to be really good for fine-tuning on other tasks, for example, NER, right? So you have this BERT network now, and it's really good at getting good information about the words at the very top. So if you feed in a sequence of words and it already captures all this useful information about it, I think it's an easy stretch to say that when you say, I went to McDonald's to get an ice cream, to continue with our ice cream example, right? There's a good chance that the concept that McDonald's is a named entity is captured in the embedding that was learned for it. Or if not specifically the idea that it was a named entity is captured, there's going to be something about McDonald's that is similar to Burger King and similar to Wendy's, and also similar to Target and similar to Walmart, and also similar to Argentina, and also similar to Joe Biden. It's that they're all named entities. It's that they're all being filled in specific contexts where they're being referenced by name. And that might be one of the high level things that's captured. And even if it isn't one of the high level things that's captured by the network, you still have these really good encodings that are separated in this super dense space. So it's easy for the model to then learn that because it's already learned such good mappings for the meanings of all these words. It's not that much of a stretch to tack on just a little bit of extra information about it, to do additional fine-tuning on now the NER data. So that's why encoder transformer models are so useful for what they're done on, but they aren't the only kind. So now we can talk about the difference between, oh, sorry, what's your question?
I'm just curious, like, is that why when you're fine-tuning, you don't need as much training data? Because, like, let's say you get, like you said, McDonald's is similar to Burger King and all that other.
Exactly.
So when you say that, oh, McDonald's is a, like, restaurant.
Yeah,
and say that since McDonald's is similar to Burger King, then you can also say that Burger King is also a restaurant.
Yeah,
So
yes.
Less data.
Yeah, that's actually very well put. That's more well put than I put it, which is that because the encodings for each word capture all this different information that's contextual, they get clustered together in ways that are very intuitive, right? And that's exactly right, that restaurants are going to all be similar to each other according to the encodings. And then also countries are all going to be similar to each other. And also people's names are going to all be similar. And acronyms are maybe all going to be similar. And the idea is it's much easier for a model to learn that, okay, if it's a country, if it's a restaurant, if it's a person's name, if it's an acronym, it's a named entity. It's much easier for it to learn that than if it's Joe Biden, if it's Argentina, if it's McDonald's, then it's a named entity, because that's way more things, way more information that needs to be learned in the second case than the first case. So that's very well put. So from good meaning representations, oh, thank you for the reminder about the CS190I section. I just missed that. Are you kidding me? It's clicking under it. Okay. So that is the encoder only training objective, which is for each word in the sequence, you can think of the model as having like this aligned column of like, here's the embedding at the bottom, and then here's the higher and higher and higher level information about it. Then at the very top, you have a good encoding for it. But then when we transfer to encoder decoder, that's where we go from the self-attention idea to the cross-attention idea. So let's say you wanted to translate from English into Spanish. You know, I went to McDonald's and got an ice cream. You still need to know what all the words mean. So it's very useful to have these encodings. And then what we could do is, let's imagine we have a model that just reads each word in the sequence and then goes, okay, what word does this translate to? So it could go yo, went, fue. I don't know. It's been a long time since high school, but it translates word by word, right? That's great if the word order is exactly the same. But what if the word order is different? You need a way to connect and look at the words in sentence A, and then as you're constructing sentence B, pick the correct ones in the right order. That's where cross-attention comes in. So that's why actually attention was originally introduced. It was for the purpose of machine translation. And this is something that I covered in the last section, so I won't go too fast over it. But that's what this example here is saying. It's showing the attention map, which is the importance of each word in the sequence, in the input sequence in English to the output sequence in French. And the interesting thing that's being highlighted here is that when the word order is the same, the attention map will be on the diagonal. So it's the agreement on the European Economic Area was signed versus l'accord sur la zone économique européenne. And the interesting thing here is that it's an exact one-to-one mapping for the first 4 words, the agreement on the l'accord sur la. But then European Economic Area starts with European and ends with area. But the French version, zone économique européenne, is the opposite order. It starts with area and ends with European. So we need a way to correctly get that. That's where cross-attention comes in. So cross-attention is basically trained the same way that we described before, but we need some way to train the model to learn to construct a sequence, construct a second sequence from the original encoded sequence. So that's where this second type of training that I mentioned here in the slide comes in. So at the top, this was a very high level diagram of this encoder only training, where we're predicting how to fill in masked elements in the sequence. The difference here is that we're still predicting mask infilling. So we still have A blank, B blank, E, but instead of filling those elements in directly in place, we have a second decoder that's producing the sequence 1 element at a time. But it's still learning to do the correspondences where as it predicts the next element, it both looks at the previous elements that it printed out and it looks at the elements in the original sequence. And it does that still through an attention mechanism, but it's cross-attention instead of self-attention. So it will, let's say, use queries from the sequence it is generating to look at the keys and values from the original sequence that it's doing cross-attention with. At a high level, that's really all you need to know. But it's this idea that we're expanding beyond and we're learning to conditionally predict. So what actually happens here in this diagram, like it's showing S, A, B, C, D, E, but what actually happens is when you run it, you'll say, okay, here's the full input, A blank, B blank, E. And the model will encode it. And then when it needs to predict it, it is literally doing it one at a time. So you always know you're starting on a sequence. So we'll feed into the encoder, okay, start of sequence. And then aligned with start of sequence, the output is the next token. So start of sequence, what do you think is the first word going to be? And it predicts A. Now, of course, it's very easy for it to predict A because we actually showed it A in the input sequence. Now that we know it predicted A, we feed that back in and we run it a second time, now with start of sequence A. What do you think the next word is going to be? Well, it no longer needs to guess A because it already said A, but it will still output A, and then it will also output B. Then you repeat it again. Feed in start A, B. Then it outputs C. That's actually what's going on here in this diagram of the autoregressive decoder. That's what that forward arrow is showing, and that's the meaning of autoregressive. Auto is in self, Regressive as in it's feeding its own output back. So it's the same objective though. You can essentially use the same loss because all you need to know to enforce a loss is where am I going to check that it did the right thing and, you know, penalize or reward it depending on if it got it right or not. And through training on this objective where we have the input that has the masks still, and then the output that is a new sequence that it has to generate one at a time, it also learns this good associative representations. And then you can use different kinds of data. So you could start off training on just this masking objective, but then you could also add noise. So maybe instead of doing, so let's do a concrete example again. I kicked the ball, right? Instead of feeding in I kicked the ball, or instead of feeding in I blanked the ball and trying to get it to predict kicked, let's feed in I licked the ball. And then at the output, so what that's doing is we're adding noise to the sequence. We're creating new noise on the input sequence by feeding in I licked the ball. And we want the model to figure out that when it's predicting the output, licks doesn't make any sense here. This should actually say kicked. So that's a denoising objective, it's called. And the cool thing about all these objectives is that they're produced only from raw unlabeled data. So we can crawl just a bunch of text from the internet and all the labels are already there in the text because we can noise it. We can just noise it algorithmically. We can do whatever bullshit we want. You know, we don't have to say I licked the ball instead of I kicked the ball. We can noise it with I Joe Biden the ball, and it would work just as well to, you know, correct it to I kicked. But the point is that you feed in some kind of corrupted sequence to the encoder, either masked or noised, and then you enforce loss on the output to, you know, hey, neural network, you need to correctly get B there in the sequence, and you need to correctly get D there in the sequence. So those encoder-decoder models, that turns out to be a good way to initialize this full model. So these two sides here of this diagram are actually the encoder and decoder. Sorry, go ahead.
So basically with like denoising, like you need that basically because if you just have your data, that's technically all positive examples. And so if you need like some negative examples to use the loss rate.
So there's not really a like theoretical reason why you need denoising. It just turns out that that is another good way to like challenge the model to figure out the right words that leads to better representations.
So that's like an alternative to masking.
Yeah, or it's a augment for masking. So what people will do in like later papers, people will add all these, they'll come up with all these different crazy objectives. Do things like, oh, shuffle the words. But the whole idea is just like some sequence in where the model will naturally be challenged to try to get what's going on in it, try to understand what the elements of it are. And then, you know, if you just train the model on like mask fill in kicked, that's good. You know, it will learn that kicked makes sense in that context. But yes, if you provide the negative example that Joe Biden makes no sense in that concept, it should be kicked instead. Does it kind of make sense why it would get a deeper representation? Because yeah, it is providing negative examples, but there's no like strict reason why it's necessary. I'm just trying to give you guys examples of what a few of the most popular objectives are. Because really half the battle in understanding these transformer pre-trained models is understanding the objective that they're trained on, because that's really how it's made. The architecture is important, but what's more important is the way that we can take all this web text data and train on it and get good representations. So yeah.
On the picture, where is it? A blank B blank.
Yes.
So like the underscores in that case are being masked.
Yes, the underscores are masks.
So
yeah.
then why like in the decoder stage, like we're getting like B following A when I thought it's something that's trying to.
Yes. So yeah, exactly. So the reason why is because in training we use what's called a decoder attention mask. So when you're actually running the decoder in real life, right? Like when you're doing the translation task, like I said before, we're generating it one word at a time. So the reason why B is hidden, the reason why A is hidden when it is guessing A on the output is literally because you're only feeding in a sequence of length 1 that is just the start token. So that the model can't cheat because it can't see the future. If you only feed in, like this is in the after it's been trained, after it's been pre-trained, and then after it's been fine-tuned on whatever your conditional generative task is. So let's say translation. Let's say you train it on a translation task, or you can train it on a summarization task using some data set. When you actually want to run it for translation, you'll feed in the English sentence without any corruption, without any masking on the encoder. And then the autoregressive decoder, first, this is all it sees. It just sees start in, and then it will make some prediction, which is A. So we go, okay, cool. Now we know that the first word in the sentence is A. We run it again with A. Then it gets B. Then we feed in B, gets C. That's why it's shifted to the left by 1. Does that make sense? Okay, cool.
I'm just curious about like why in the encoder phase we have the A playing B playing E. So it's like not in the A, B, C, D, E order.
Yes.
It's in the A blank B blank E order.
Oh, you know what? That's a great point that I actually missed. One of the other advantages of this bidirectional, of this like encoder decoder sequence is that you can feed in fake masks. So you can feed in a mask that is of indeterminate length. So not only does the model need to know, like when you do this objective, you are telling the model there is exactly 1 token that is missing, figure out which one it is. There is exactly 1 token that's missing here, figure out what it is. But in this case, you're saying there could be something here, could be 0, could be 1, could be 10. There could be something here, could be, and then it has to figure out, okay, I don't think there's anything here. I don't think there's anything between I and kicked. So it just predicts I and then predicts kicked. And then here, I kicked blank blank into the net, right? You wouldn't say I kicked ball into the net. You'd say I kicked the ball, or I kicked a ball into the net. Okay, this is probably 2 tokens. So it has to do C and D to fill in there, because contextually it doesn't make sense to go in a single token. So thank you. That was actually, I didn't even catch that because I was going over this so fast. But yeah, that's another advantage and that's another actually part of the encoder decoder masked language modeling objective, is that the masks can be of indeterminate length. Okay, so, but the way that the autoregressive is trained makes sense to everyone. Great, because it's exactly the same in decoder only. But the idea in decoder only is we just want it to learn in the forward direction to generate text. Just from looking at what it previously generated or what it previously saw in the past. And that's how like ChatGPT works. So ChatGPT is just trained on so much web text, and it's seen so many conversations and so many examples of like, this is what a story looks like, that it just gets very good at, okay, I've seen it was a dark and stormy night. I'm going to say, and then someone asked, it learns high level structure because it's a giant model with many, many layers, and it's just trained on so much text. So that's decoder only. And once again, in the decoder only, the autoregressive training task is, you see 1 word, what is the next word? Then you feed that word back in. You see those 2, what's the next one? But just without any conditioning on a separate sequence. So using this for translation is not going to be as good as using this for translation. And using this for classification is not going to be as good for using this for classification. But maybe using this for open-ended generation is more efficient than using the other structures for open-ended generation. Because in each of these different structures, so this is the way that BERT works, this is the way Roberta works, we're isolating the component that we really care about for that given task. So in the encoder only case, we're isolating the part that is learning what each individual token in the sequence means. And we're just using that part because that's all we care about if we need to classify, is a word a named entity or not. And for this part, we need the whole transformer architecture, because if we want to translate, the most efficient way is going to be, we need a part that figures out what the first sentence means, or we need a part that figures out what the input in language A means. Then we need a part that guesses in order what the words are that mean the same thing in the second language. So it makes sense to have both an encoder and an autoregressive decoder. And then if it's just open-ended text generation, we can just use the natural conditioning that happens because it needs to look backward to the previous words in the sequence to not repeat itself and stuff. Yeah.
So with the GPT model, so the bottom diagram,
Mhm.
if you start off with nothing, then you just start off with start cooking, right?
Yeah.
It's the GPT modeling where you start off with like
With the
that
prompt.
would be question answering though. Like this is GPT itself isn't used for like question answering, right?
So it can be. And so you're probably wondering from this description that I gave, if you've played with GPT, you know that it can do a lot of things surprisingly well. So, GPT can translate things. If you feed in like, oh, here's a sentence in Spanish, translate it to English. Or if you ask it a question, it can answer a question. The answer for why it can do that is basically that the model is so big and it's trained on so much text that it's basically seen everything. And then they also include examples. So they're like, okay, we'll train it on an example of a translation task. And that is possible to do, right? Like it's possible to show the transformer, okay, English : English sentence, Spanish : Spanish sentence. And then if you want to recover that ability, you just feed in as an input English : English sentence, Spanish : nothing. And then let it do the next word thing. And there's a good chance it will fill in the Spanish sentence. That's what the idea of prompting is. And that's basically relying on it to just recover all the information that it has fit to from its internal elements. And it's very hard to interpret or understand where all that information comes from. But it just turns out that the more text you train on and the larger the model is, the more it can quote unquote memorize. That's the term that we use in the research community, actually. And then you had a question?
Well, yeah, I was still a bit confused about encoder decoder.
Yes.
So I kind of get the first part, which is like the encoder is for the self-attention.
Yes.
And then I kind of got lost with the cross-attention part.
Okay.
And then like, what are you doing when you translate to like the French language?
Okay. Yeah. So I can go in a little bit more detail for that. So notice how this side is the encoder and this side is the decoder. The encoder side is much shorter than the decoder side, right? That's because there's actually two different attention modules that are both being used in the decoder side. Only an encoder decoder. This actually does not apply for decoder only, annoyingly, but it has this masked multi-headed attention, multi-headed self-attention, which is just looking at the input sequence. And then it has the same multi-headed attention that we have in the encoder sequence, but it gets to see all of the elements in the input sequence, as well as all of the elements that it's seen so far in the decoder sequence. And the idea that these three arrows are showing here, it's a little bit confusing, but this is the query, key, and value, right? So that's to get into the nitty-gritty. And we discussed this a little bit last week, but it's definitely helpful to go over it again. This is the actual attention function that is finding how important each word is to each other word, where the elements of the attention function that are learned, the actual dot product itself, that's not a learned parameter. That's just, dot product. But the actual values for this query vector, this key vector, and this value vector are all learned. There are additional learned parameters that apply for every single layer, where it's saying, okay, if I have some embedding, I need to convert this into a vector that when I multiply it by vectors that are important for understanding the meaning of this word, it will get a high dot product. And if I multiply it by vectors that are not important, it will get a low dot product. So this is very abstract and high level, but the idea here is that we can look over a whole sequence, and in the case of self-attention, it's the same sequence that we're doing this dot product attention pairwise between every element. So in the case of I kicked the ball, for the self-attention, we can check, okay, what is the attention? What value do we get for the attention, aka the importance of I to I? Probably going to be high. What are we going to get for the importance for I to kicked? What are we going to get for I to the? What are we going to get for I to ball? And it goes through the entire sequence and computes this pairwise attention for every single one. That is where this attention matrix comes from. But this isn't showing the self-attention. This is showing the cross-attention. So that's the way that the correspondence gets computed. The idea is that the same query and keys, which are always learned, rather than getting applied pairwise to every element in the input sequence, get applied pairwise between the input and the output. But the same summing and multiplying that blends all the information together still happens either way. This isn't super important to understand for like the final or anything, by the way. So I'm just like, don't worry if you don't get this part, but I am trying to satisfy your curiosity. But that's what this part of the diagram is showing. It's showing that the query and key is being fed from the input embeddings, and specifically from the top of the stack. The idea, or actually, I'm not 100% that's true. So it's either going from, okay, from the bottom encoder layer and the bottom decoder layer, let's share those keys, you know, and then next layer up, or it's going just from the top and looking at those all the way in. Off the top of my head, I'm not 100% sure, but at a high level, that detail does not really make a huge difference. Yeah.
So just like super simply, I get a little bit lost. Like for the encoder, it's English, right? The one that
Yeah, in the case of translation, let's say the encoder would be an English sequence and the decoder would be a French sequence.
and you know the French sequence too.
Yes, so during training, you do know this French sequence.
Okay.
And then it's learning the same relationship. Like what word, like if I need to predict the next French word and the next word is zone, whatever, I don't speak French. The next word is zone. The English word that matters to predict that is area. So once again, you know, when you provide both of those sequences in training, and it sees many, many, many of them, including many that all contain area and zone, it will eventually fit to the function that, okay, the query for the French word zone needs to connect to the key for the English word area.
So there's also an encoder and a decoder there, right? Because you did
Yes.
figure out the French. Oh, okay.
Yes, exactly. So the French embeddings are getting handled by the decoder. But the decoder, actually, the decoder shares the structure of the encoder, but it's being trained on a different objective. But you see the decoder has the bottom and top parts are actually the same, but it has this middle part where it's additionally adding information from the encoded sequence. So it's blending together information from the whole encoding sequence, which you can see the entire thing at once, and from the decoder input sequence, where it can only see the past values. So it's saying, okay, I know that I translated the European Economic Area is, and I know that I've generated La Zone Économique. What's going to be the next one? European. And it learns over many, many sequences that that combination is how you get the right words out. At a high level, that's what's going on there. And it's not super important, I think, to really understand that. The thing that I really think is important to drill home is the difference between the objectives. So GPT, decoder only, if it only generates, the only thing you're training on is this autoregressive. You guys should write this down. The only thing you train on is the autoregressive forward language modeling objective. So in other words, look at the first 5 words, predict word number 6. Look at the first 6 words, predict word number 7. Look at the first 7 words, predict word number 8. That is GPT. That is decoder only. Encoder only. So Bert, Roberta, etc. You want the model to output good representations for each word. So you train that on the masked language modeling objective, where you show it the whole sequence at once, but you hide B and you hide D, and the model knows there is one word here for B, there's one word here for D, what are they? And then the objective that it's getting trained on is to predict them. And encoder decoder is you feed in the sequence with masks or noise or both of an indeterminate length. And then the model needs to predict, also one word at a time, the uncorrupted sequence. And it needs to figure out, okay, this mask is actually length 0 because A and B make sense together. This mask is actually length 2 because it's missing 2 words. Those are the ways that these 3 different objectives differ. Okay, what was your question?
So is it encoder only model the same thing as an encoder only model except recurrent? Because couldn't you just take the encoder and then say, and mask out the last, like start with A and mask out the second one and ask it to predict that, and then you take that and then you ask it to predict a third one? Like,
That's a great question. It almost is. The key difference is the decoder attention mask. So this is something that I haven't mentioned yet, but there are, and it's actually not even depicted in this figure, but you can also apply an attention mask where within, and that's actually shown here, where this is like the diagram of what happens with query, key, and value. And it has this bit here of mask optional. The query and key is the pairwise comparison between two elements in the sequence. So in the case of encoder only, we're not going to do any masking because we want to allow the model to see into the future. By see into the future, I mean, if we want to predict whether you licked the ball or kicks the ball, you need to know that the ball comes at the end of the sentence. Just from you can't tell what that word is going to be. But when you're training it on this objective here, where we show it and then A, start of sequence and then A, and then start of sequence A to AB, when we actually train this, we don't do the autoregressive process I described. That autoregressive process where we're predicting one at a time, that's what you do during inference time because you don't know the whole sequence. But during training, you know the whole sequence. So what we do is we enforce inside of the attention mechanism. We do not let the sequence at this location see the future. We only let it see the past. So we feed the entire sequence in at once, but we mask it in such a way that to predict the first token from start of sequence, it doesn't get to see ABC, but we let the one that is predicting on top of A see A as well as start. Then we let the one that's predicting C see start AB. We let the one that's seeing C or that's predicting D see start ABC. So it gives you this shape where you have a matrix for your attention mask, and that's what's being shown here in a really small figure. Is that like if this is like word in the input, and then word we need to predict, we only let the let me think about this. Yeah, okay, so this is input and this is the prediction. We only let the prediction for the first word, we only let it see the 0 input, the very beginning of the sequence, but we do not let it see any of the other words in the input. But for word 2, we still let it see the input, but we also let it see the word that it previously depicted. So that gives us this triangular matrix of all 1s and 0s on the top. That's what this mask is. And that is getting enforced when you train the decoder only model. But it's not there when you train the encoder only model. That's why they're different. That and the objective. The fact that in the decoder only objective, the things that you're predicting are aligned in the sequence with where they're actually located. Whereas with the decoder only, the outputs that you're predicting are shifted left 1 from the input sequence. Those are the two differences. And so this is how we force it to learn through a training process that is otherwise identical to the bidirectional encoder. We force it to learn by having different prediction targets enforced, and by having this mask, we force it to only look backwards in time to predict the single next word in the sequence. So, okay, we have 10 minutes. So yeah, okay, another question?
I have so many questions.
That's fine, that's fine.
So is the decoder phase actually using like long short-term memory RNN like within it somehow?
So this is using just transformers, which are once again only using the attention to transform the sequences. LSTM is different. Long short-term memory is different because what it actually has an internal memory where it learns when it's seeing an element in the sequence that's important, it updates it. At a high level, that's the difference. And it's that it's also recursive. It also takes in its own input. So this is a different model, but in principle, there's actually no reason why you can't train an LSTM on these objectives. And in fact, that actually connects all the way back to William's slides. So remember in William's slides, when he's talking about Elmo and talking about BERT, Elmo, the first thing that William introduced, and actually chronologically, the first thing that came out is in fact exactly what we talked about. It is a decoder-only language model, but it's trained using long short-term memory instead of using transformers. And it just happens to turn out that transformers are better at handling this long distance context than LSTMs are, because LSTMs have to update their internal state every single time they see an input. So they have this problem of catastrophic forgetting over time, where if maybe a word at the very beginning of the sequence is super important to know what the word at the end of the sequence is, an LSTM runs the risk of only looking at the close context because it's saying, okay, do I still need to remember I? 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 And maybe it will get super far at the very end. And then you mask a second I was disappointed, let's say. I was really thirsty on a hot day and I went to buy an ice cream, but the store was closed. Blank was disappointed. Maybe for a transformer, it's trivially easy to see, oh, I was disappointed because there's I at the beginning here. I've learned that the query for I connects. But maybe LSTM goes, okay, do I still need to remember that I was at the beginning? Do I still need to remember? Do I still need to remember? And then eventually goes, you know what? All this is about, all the last few words have just been about the store was closed, whatever. I don't need to remember I. Then it gets to blank. That's the difference. Okay. But yes, it is entirely possible to train other network architectures on these same objectives. It just happens to be the case that transformer networks perform the best. But in the future, we might discover a better architecture, but there's a good chance that the same objective is what we're going to use. Okay, so are any other questions? Now you can just ask me general questions as well, because we're almost out of time. And I'll also have office hours the day before the exam, and Alex will hold a special section on next Tuesday. But yeah, any other questions? Yeah, go ahead.
Well, what's the most important thing to take away this section?
Okay, most important thing to take away is what I just said, and I'll even make a note of it. The thing that I said here about I described four things, four different objectives, including encoder only, encoder decoder, decoder only. And then I described out of those four, there's the forward, you only look in the past, predicts the next word. That is decoder only, that is GPT. You feed in a sequence of blanks and then you ask, given this blank, this specific blank is one word, what word is it? That is encoder only. That's called masked language modeling. And then for an encoder decoder model like BART, you feed in blanks, the same, you can do the exact same blanks that you did for encoder only, but they can be indeterminate length. And you can also noise the sequence and have the model try to correct the noise. So those two types of training objectives go to encoder decoder. Only the forward direction, look in the past, goes to GPT. That's the key. I think that's the key takeaway that I want to impart on you guys, because understanding the objectives is, I think, the most important thing to understand for these pre-trained models, more important even than really understanding the transformer architecture. What's your question?
For the encoder and decoder model, I know you said that when you're predicting, let's say, start token or A, you only have access to previous generated
Yes.
words. But do you have access to the whole input from encoder?
Yes, exactly. You do have access to the whole input from the decoder. So these are the pre-training objectives, right? But this, once you have a pre-trained model, you can also fine-tune it. So let's say you've pre-trained a great encoder decoder model where it's learned on this, mask infilling and denoising and stuff, and you've trained it on English data, you've trained it on French data, you've trained it on Spanish data. Now you want to train it to be a translator. Now you need supervised data. So you can no longer just crawl from the web, because there's not very many examples on the web of this is the text, this is the exact same text, but in Spanish. So you use the few examples you have and you fine tune this pre-trained model, where now the objective is we're not going to mask anymore. We're just going to feed the whole English sentence in. And then we're going to feed into the decoder the whole Spanish sentence. But once again, the decoder can't see the future because of the attention mask. So it can't cheat. It can only look at the entire English sentence. And that's how it uses all the information from the encoded sequence, even to just predict the first word. But in the case of just a decoder only, like GPT, it doesn't make any sense. Like, you can ask GPT to generate from nothing, but why? You know, you're just going to get random garbage. So you have to feed it some initial prompt sequence that says what you want it to do. And then it's going to go, okay, what's the most likely thing that's going to follow this up? Well, the most likely thing that's going to follow a question, you know, Q the question, A : blank, probably going to be the answer. So that's how GPT learns to, you know, answer from a prompt. Okay, any other questions? Yeah, keep going.
Noise for encoder only.
So I think you actually can noise for encoder only. Yeah, I mean, you can. I think it's more popular for encoder decoder training than it is for encoder only, but it definitely also gets done for encoder only training. But the classic best way to understand is this like mask infilling. So I think that's why it gets emphasized more. And I know BERT, I'm actually not 100% sure, but I'm pretty sure BERT is only trained on the masking. But maybe it does have the noising, but either way, you can do both. But the important thing is you can only do the forward direction, look in the past, predict the next word for decoder only. It wouldn't make any sense to do noised input for a decoder only. Yeah.
So why would we not want to use encoder decoder models for everything when it can do both that encoder models can do on its own and decoder models can do on its own?
Basically, well, okay, so there's a couple of things. That is actually, so before GPT-2 and like GPT-3, the big like pre-trained models that were like, we are going to do zero-shot performance. The original thing that was proposed by Google was T5, which was actually an encoder decoder only, or sorry, encoder decoder model that they just trained on a bunch of different tasks. And they would train it, okay, given the input, translate English to German, that is good. Okay, the output is das ist gut. And they trained it on all these different tasks with the same idea being, oh, well, we can prompt it. You know, we can give it a prompt where we ask it to do this specific task, and it will learn to attend. Okay, the beginning is very important because that's telling me what the task is, and then I can engage my capabilities. It just turns out that this approach is less efficient than the approach of putting all the parameters in to the decoder. Because if you think about it, there's going to be waste where you need to train separate parameters on the encoder and on the decoder, where both of those parameter sets are learning the meaning of the input tokens, right? It's more efficient to just do that once with just the input only, with just the decoder only. So that's why for open-ended general pre-training, I think the more popular approaches are to use decoder only style for like open-ended generation. But for task-specific things, so if you know you're doing translation, it is probably better to do encoder decoder because it's more efficient. Like if you were just going to make an English to Spanish model, you can train the decoder on Spanish only, and you can train the encoder on English only. And now that's actually more efficient because the parameters for transforming the embeddings of the input on the decoder side don't have to share space with the English words and the Spanish words. But yeah, good question. Okay, other questions?
So when you say it's more efficient, basically it's more costly to do it, I guess?
Yeah, exactly. And more costly in terms of like number of parameters, or maybe more costly in terms of like how many parameters you need to get to a same performance. So like, let's say we have a performance target of like, oh, I want the language modeling loss to be X%. Maybe you need, for some tasks, you need more parameters to do an encoder decoder to accomplish the same thing as a decoder only. But for other tasks, it would be, you know, you need fewer parameters. And having more parameters is a big problem because you need a bigger GPU, a more expensive GPU to, you know, run the same batch size.
So it's actually doable, then the encoder decoder models still perform better than.
So once again, it just depends. So another example of why maybe you wouldn't want it is just for like open-ended creative text generation. You would be feeding in an input that's just going to be like this long of like, this is the prompt. And then the decoder is just starting from there, generating words at the output. Really, also this is like a very philosophical thing. Like there's not a strong like scientific answer to some of these questions. And it eventually just boils down to like what company invested their resources into doing what. So now that OpenAI has spent so much money on training a decoder only model, they're kind of locked in on that direction. And it makes sense for them to invest in scaling it up and pushing further. But also for things like bounded specific tasks like translation, it is better to have the encoder decoder. But for just general generation, it's more efficient to do decoder only because you don't have to learn twice how to learn what words mean. Whereas both the encoder and decoder both have to separately know what all the words in their sequence mean. That's, I guess, the reason why sometimes it's better to do decoder only. Yeah.
I think the encoder only and the encoder decoder model, they sound very similar. So what's the difference between the two?
So mainly the difference is what kind of tasks you can fine tune for them. So you can't make an encoder only do translation because it is not trained with this bias, with this inductive bias is the term we use in the architecture to be able to predict the next word, because it's always making predictions in line in the sequence, right? So it's predicting, oh, this word goes here, this word goes here, in between these two. But it's never learning, okay, I've seen these three words, so the next one is this one. So you can't generate text from an encoder only. You can only classify text. But sometimes we want to classify text. And, you know, in those cases, like sentiment classification or the NLI is another task that I know William described, where it's sentence A, sentence B, do they contradict each other or entail with each other? For tasks like that, an encoder only is great. But for tasks where you conditioned on some text or conditioned on some input in some modality, you want to generate an output in another modality, encoder decoder makes sense. But for the same modality, I just want to generate stuff, decoder makes sense. Because another application of encoder decoder, like you know how I've been saying that these inputs, they're just sequence elements. They aren't necessarily words. One application of encoder decoder is actually to have the encoder take in pixel data, but the decoder be trained to predict words. Then in that case, you can train a captioning model where the input is just seeing, okay, these are the pixels that are in the shape of a dog. So the decoder can then go, oh, it's a picture of a dog. So that's another thing that's useful about encoder decoder is that if you have two completely separated modalities, it makes more sense to do that. But if you're sticking in one modality, it often can, depending on if you want to do classification or generation, it can make more sense to do encoder only or decoder only. Yeah.
Just out of curiosity, would BART or BERT perform better for named entity detection?
Will BART perform better than BERT for named entity? Off the top of my head, I can't say confidently, but I would guess that BERT or Roberta or some encoder only would be better for named entity recognition. The reason being, so what you could do is you could fine tune, for example, BART to say, okay, I'm going to feed in the whole sequence and you just output for me, just output the list of named entities. So I'll feed in, I was really hungry. It was a hot day and I went to McDonald's to get an ice cream. And then the output will just be McDonald's, end of sequence, because that's the only named entity. But if you wanted to train an encoder only for it, you could train on a different objective, where for each element in the sequence, you go, oh, named entity, oh, right? Like those are two different ways to train the same thing. My intuition would be for this one, you're actually giving it more information, for example. So maybe it would be better to do encoder only. But these architectures are flexible, so you can train them for like a lot of different things. Okay, so yeah, we're a little bit over time. So I'm gonna stop the recording, but if you guys have any other questions, you're welcome to ask, because I know it's gonna take forever